everybody. So to finish up this discussion of plane symmetry, let's try to say something about this fact that there are 17 wallpaper groups. So if you'd like to read about the proof, it's in a paper called The 17 Plane Symmetry Groups by R.L.E. Schwarzenberger, published in the Mathematical Gazette in June 1974. It's available online. And it's a paper which everything that you need to know to read this paper, we have covered in this course actually by this point. So if you're curious about the proof and you want to take this on as a project, I recommend it. It's not, it doesn't require a lot of more abstract mathematics than you already know, but it does involve a lot of careful case-by-case checking. And so you make a lot of assumptions and you work your way down through this tree of possibilities, and eventually you show that you found all the possibilities that there are and you get 17. You produce the table that you saw in Schattenschneider's article. Now, I feel like we should prove something, and I don't want to prove this full result because it would take probably, I don't know, a couple weeks worth of class time to work through all the details. But as Schwarzenberger says in his introduction, neither the passive contemplation of wallpaper patterns nor the passive contemplation of abstract definitions is mathematics. The latter is above all an activity in which definitions are used to obtain concrete results. So we should at least do something that's actually mathematics. And what we're going to do is we're going to prove a partial result. The first step in the classification of these 17 groups is to imagine that the point group has no reflections or glide reflections. And if you assume that, then that means that the only thing that the point group can have is rotations. And we know that if it has rotations, it has to be a cyclic group generated by a sort of a smallest rotation. And we're going to prove that if there's no reflections or glide reflections, then you have to have one of 5 possible lattices, depending on whether your point group is cyclic of order 1, 2, 3, 4, or 6. And here are the 6 possibilities. You could have a square lattice, which has 4-fold rotational symmetry. You could have a rectangular lattice, which has just 180 degrees rotational symmetry. You can have what's called a rhombic lattice, where you notice that this is 120 degrees. And so this has 3-fold rotational symmetry. And you can have just a random parallelogram that has no extra symmetry, or you can have the hexagonal grid, which has 6-fold rotational symmetry, and that's it. If you want any of the more complicated symmetries to get up to 17, you're going to have to introduce either reflections or those glide reflections, or some combination of them. So where did this result come from? Well, we're going to prove it. It's not very difficult. We're going to use, however, a fact which I'm not going to prove, which is that every lattice contains a shortest vector. And this is completely believable, I think. If you think about the pictures of a lattice in the plane, it's a grid of points. And it just seems clear that you can't have a grid of points that gets arbitrarily close to the origin. There must be a shortest. Here's the origin, and here's my grid. Then there has to be a point which is as close to the origin as you can get, and not points in the lattice which get arbitrarily close. And the reason I'm not proving this is that although it's not a very difficult thing to prove, it's really a fact from calculus. And so we're just going to assume it since this is an algebra course. And so let's assume that we have a lattice L, and we have a rotation that preserves the lattice. And so we know that the group of rotations is cyclic and generated by a rotation through 2 pi over n radians for n equals 1, 2, and so on. And so we're going to let r be the rotation through 2 pi over n. And we're going to let t be a shortest vector. So if t is the shortest vector, we have a picture that looks like this. Here's t, and here's rt. And by assumption, this is in the lattice, and this is in the lattice. So the vector joining them is in the lattice. This is rt minus t. And because t is the short, and so first of all, the length of rt is the same as the length of t because the rotations are orthogonal transformations. And also the length of the distance from rt to t has to be bigger than or equal to the length of t because t is the shortest vector. So if we have another vector in the lattice, it has to be at least as long. This means that we have the norm of rt squared minus 2 times the dot product of rt with t plus the norm of t squared is bigger than or equal to t squared. And that means that t squared plus t squared minus t squared is bigger than or equal to 2 times the dot product of rt with t, which is 2 times the norm of rt times the norm of t times the cosine of theta, which is 2 t squared cosine theta. And this side is t squared. So if you put those two things together, you get that the cosine of theta is less than or equal to 1/2. And if you want the cosine of 2 pi over n to be less than or equal to 1/2, you get that n has to be 1, 2, 3, 4, 5, or 6. Because if you look at the graph of cosine, here's 2 pi over 3, 2 pi over 6, which is pi over 3, which is 60 degrees. 2 pi over 7 is here, 2 pi over 8 is here, and so on. This is 1/2. So all these other points have cosine too big. So the existence of a shortest vector that's preserved by the rotation immediately cuts you down to n being 1 through 6. And we already know from our pictures here that 1, 2, 3, 4, and 6 occur. So our problem is 5. It all boils down to 5. And the cosine of 2 pi over 5 is less than or equal to 1/2, so that's not a contradiction. But there's a trick. Namely, we look at this picture, and we, instead of looking at t and rt, we look at r squared t and minus t. R squared t is rotation through 4 pi over 5, which means that this angle here is pi over 5. And if we look at this triangle, we have a vector minus t and the vector r squared t. Both of these are in the lattice. Therefore, this vector which joins them, r squared t minus minus t, is in the lattice. And this angle is pi over 5, which is 2 pi over 10. And if we use this law of cosines argument that we did here, you notice it's really the same picture as we have here. But we have 2 pi over 10. Then we already know that we're gonna get this contradiction here, because we're gonna get that cosine of 2 pi over 10 is less than 1/2, bigger than 1/2, bigger than or equal, bigger than 1/2, strictly bigger than 1/2, and that's going to force this vector w is going to end up being bigger than t, which is a contradiction, less than t, which is a contradiction to having the shortest strictly less than t. So 5 can't occur. So that settles the fact that at least if we eliminate reflections and rotations, then these lattices that we probably already know about, the tilings that you see for floor tiles and so forth, those are the only possibilities. And to continue with the analysis, you now have to introduce into this, because after all, any plane group is going to contain rotations and a lattice. The question is, what else does it have? And it may have some reflections and some glide reflections. If you were to go back to Schatten-Schneider's diagram, the lattices that correspond to these basic ones are the ones called P1, P2, P4, P3, and P6. Those are the ones which have translations and rotations by 1, 2, 3, 4, and 6, and no other symmetries.